Okay, so should we start? Okay, I will start.
Okay.
So I'm recording. Okay. Good evening, everybody, and welcome to our special session. So today I would like to welcome Professor or Dr. Mark Miller. He is a very renowned person in the field of AI and education. And as you can see, I'm sharing I will just, okay. Okay, so he's sharing. So he has a PhD from MIT, and he is one of the veterans in the field of AI. And today we are fortunate that he has agreed to give us like valuable time. And he will be talking about AI in education, which is again a very good topic and very hot topic. At the same time, very important topic also, as people are now, since this chat GPT came into picture, people are mostly concerned about that how AI should be used in education or not, or how it can be used. So today I'm fortunate and that we have Dr. Mark Miller to give his perspective on the like AI in education, and he is one of the veterans in his area. Okay, and welcome, Dr. Mark Miller. And now stage is to you.
Thank you very much. Appreciate the nice introduction. So yeah, I'm going to share a slightly different version of a presentation I gave earlier today to 200 high school teachers and their students. Because this is now, we've gone from where most people didn't know what AI was to suddenly everybody wants to know what is it and what is it good for. And I mean, we already know that it's good for weapons, unfortunately, but we also like to look at some of the positive uses for the world. And certainly one of them is education. And that's been my passion since I first heard the word AI. So I want to talk, first of all, um, what is it? How did we get here? And how can it be used to improve education? And of course, preparing students for a high-tech future also means they need to know about it. It's not just a matter of that they need to be kind of subjected to it. They need to know how it works and how it's going to change the society as well. They need to understand the benefits and risks and what does it mean for future careers. And actually, pretty much all of us need to understand what it means for future careers because some of the things we've seen suggest that we might need to think about whether we'll be looking for a new job too. So anyway, so you got my name and there's my email address. You're welcome to email me. I actually do two things. I run a nonprofit called Learningtech.org that helps schools with technology. And I'm a part-timer at Northeastern University in Silicon Valley, where I teach computer science, basic kinds of stuff, as well as an elective called AI in education. Okay, so I want to start with some things I learned from my grandfather. Uh, my grandfather took a special interest in introducing me to science and technology. He was a blue-collar worker who worked his way up to a plant supervisor of an engineering plant run by the Western Electric Company that made incandescent light bulbs. And what he realized, and part of his success of his career, was that learning about math and science and related fields, electronics, was a key part of his success in life, and he wanted to pass that along to his grandchild. So he did things like required me to learn how to take the square root of a number by hand on a piece of paper or on a whiteboard, or actually it was blackboards then. Or after I did this, like, well, now let's do cube root and so on. He also helped me build a 5-band shortwave radio, where I learned a certain amount of electronics and a lot of soldering. And at one point, he introduced me to this analog computing device, also known as a slide rule, and made sure that I learned what every scale did and how to use it. And also things like how to estimate what your answer should be so you could check the reasonableness of your sliding back and forth. So I think I was probably the last student going to MIT to actually have a slide rule. And by then I had a big circular slide rule because they were more accurate. And of course, it never turned out to be useful. in my classes. So in some sense, some of what I learned from my grandfather didn't stand the test of time. But some things did. And one of them was his passion for science, technology, engineering, and math. And that actually was life-changing for me and helped me figure out what did I want to do with my life. So part of my story is about there's a lot of things happening at a very fast pace, and it's going to continue at a fast pace. And it's important to figure out how to learn and what to learn so that what you learn will actually stand the test of time. And it turns out that it's more about, growing up with an adult human who really cared about you and who believed that you could do these kinds of things. So as we try to bring AI to education, we don't want to forget about that human relationship element. At one point, I thought teachers wouldn't be necessary anymore, and I've since realized that I was pretty wrong about that. Okay. All right, so what is AI? It's the science and technology of making machines do things that would be considered intelligent if done by humans. So AI studies algorithms, data representations, and models required to support things like perception and reasoning and action and learning. So it overlaps with cognitive science to some extent, because in cognitive science, we're trying to build formal models of how human intelligence works. But on the other hand, it also overlaps with data science and software engineering, for that matter, because if we're basically focused on using data to achieve optimal results from a machine, and we're not trying to model human problem solving, that it's a different goal and possibly a different way of achieving it. So early AI was based on, and this is my era, was based on hand coding symbolic representations of knowledge and algorithms. And this was in the 1970s, where we'd just come from realizing that computers were more useful than just doing numerical computations that were really large and extensive. They could also be used to represent symbolic things. So the era before was like scientific computing and business computing. Everybody used Fortran for scientific computing and COBOL for business computing. When we got to AI and symbolic computing, most people used a language called Lisp, which probably many of you have not heard of. It has lots of parentheses, but it's actually a very, very powerful language. And I spent a lot of time programming in that language. So that was the early AI. The modern AI is very different. It's based on machine learning algorithms, including what we call deep learning. And you hear lots of new words every day. The one that's currently caught a lot of attention is transformers, particularly generative pre-trained transformers that serve as foundation models from which you can then build other things. Before I forget to mention it, please post questions in the chat. I may not notice the chat, but I will count on Professor Gupta to call my attention. We can answer questions as we go. Sometimes I'll be about to get to that anyway, and then we can maybe postpone it for a slide or two. Okay, so in the early days, the way that we determined whether or not we had successfully built an AI was a test that was designed by Alan Turing around World War II, called the Turing test. And the Turing test was, if we have a computer in one room and a human in another room with a keyboard, and you're at your computer in a third room, and you can ask questions, any questions you want, but both the human and the computer are allowed to try to lie and trick you and so on. So the computer might deliberately take a long time to add up a big number or something. If you have as much time as you want and you can't figure out which is which, you're basically guessing at the chance level, then you have to say, well, then the computer must be intelligent. So that was the basic idea. Well, it turns out we've kind of achieved that, and yet we don't feel that we're there, because now we're realizing that it's a little bit more than it sort of seeming intelligent or pretending to be intelligent. It's not, I mean, the systems we have now are not only not self-aware, but in many ways, they really don't understand what they're talking about. They're able to generate sentences that sound like they understand it, but in fact, they don't, because we know how they work. So we need better tests. But in the earliest days, this is right before I got to MIT, there was a chatbot called Eliza. This was in 1966 that pretended to be a Rogerian psychotherapist. This actually is a good example of why the Turing test isn't adequate. People would actually pour their hearts out to it for hours. And it was using very simple pattern matching to take what they said and turn things around and give back an answer that made sense. And some of the patterns were just clever tricks that were put in by Joe Weizenbaum. For example, if you told it you hated your mother, it had a special built-in response. It would say, well, tell me more about your family. People would buy it, you know? And so he actually became very disillusioned about AI. Nowadays, of course, we have ChatGPT, which was announced in late 2022. And it has a lot more knowledge and uses more sophisticated methods to decide how to respond. But yet you can talk to it for a long time and get a lot of really useful answers to questions and so on, but yet you still feel like it doesn't really understand what it's saying. And talk at that. So I want to just step back a bit and say, let's look at the early approaches to AI a little bit more closely, and how well did they work, and how did we get here from there? Well, one of the things was that because these were hard systems to build and we didn't know a lot yet, we didn't try to take on full applications at first. We took on what we called micro worlds, little game programs or micro worlds. And one of them was called the Blocks World. And this was a program by Terry Winograd that could put up on a display, and the graphics were pretty primitive, a set of children's blocks. And they were different colors and different sizes, and some were triangular and some were square. And you could tell it things like pick up the big red block and put it in the blue box. And then you could say how many blocks are inside the blue box, and it would be able to answer correctly and so on. So it was somewhat impressive, but it was still a miniature world. Games like chess were very, very popular. And the philosophers were very skeptical of us because they would say, well, maybe you can get it to play chess against an average human, but you'll never get it to beat a chess master. And so then Deep Blue comes along. This is 1997, and it beats Garry Kasparov, who is the reigning chess champion of the world. So then the philosophers came back and said, well, okay, so chess is easier than we thought, but you'll never get it to play Go, because Go is a much more complicated game. And it took a little later, and it started to involve some of the modern AI. But in 2016, a program called DeepMind beat Fan Hui, who was the reigning Go master of the world. But the other things we did, and this was important to how we built these systems, we would take something as simple as tic-tac-toe and play it against children who weren't old enough to know that if it's played correctly, it always ends in a tie. They didn't know that. We would say, just talk out loud as you make your move. Why did you decide to go to the center square? Why didn't you go to that corner? Or which should you do first? Should you block your opponent being about to win, or should you take your own win first? The order of rules mattered, and a lot of these things were represented in a sort of an if-then rule format. So first there were little toy systems, and then there were systems that could actually do something interesting, always in what we call a narrow world. So if you talk to, I'm going to talk about this system called Mycin, which was for a subset of medicine. If you asked it, who won the NFL championship or something, it was just like nothing. It can't do anything, right? But if you provided the data in response to its questions about a patient who had a bacterial disease, it was pretty good at diagnosing and actually recommending treatments from the drugs available at that time. It was, in fact, better than most MDs. It wasn't better than the very best MDs, like Ted Shortliff, who built it, but it was pretty good. And so if you were in a remote rural village in India or Africa or parts of the world where you didn't have as much access to healthcare, it could be good enough. It could actually help save lives. Another example, this was in the world of high tech. That's a picture from the Computer History Museum of a DEC VAX 11780. That's a computer that I actually used. The program was called R1, and it was an expert system, is what we would call it, or a rule-based expert system. Its job was to configure the order for a large mainframe system. So if you ordered 11780, they would ask you, how much disk space do you need, and how much memory, and how many processors, and you'd have to figure out as a sales engineer, well, if they're ordering, 3 banks of memory, we're probably going to need a bigger power supply in another cabinet, and so on. Problem was is that the sales engineers were error prone, and what would happen is a few months later they would deliver this giant computer, and they wouldn't be able to get it fully up and running because they need to order some more parts, and those would be on back order and so on. So they built this expert system based on rules like, if you need more RAM, if you need more than one thing of RAM, then you should add more power supply. The simple rules like that, and this system was actually better than most VAX 11780 sales engineers, and so it actually improved customer service. This company was eventually acquired by DEC, by HP, if you're curious. So that was kind of the AI of the time. How was it used for education? I want to give 2 examples, and they represent significantly different approaches, almost kind of, I don't quite want to say adversarial, but kind of competitive approaches. And I happen to work on both of these examples. They're not necessarily the most significant or most important, but I know about them personally. Logo was actually pretty significant. This was a programming language for children. It came out of an educational philosophy called constructionism, which was developed by Seymour Papert. And you see Seymour Papert in the picture there with what was called a floor turtle. So constructionism came out of work of Jean Piaget, which he called constructivism. The idea was you can't just pour knowledge into a student's head. You have to give them opportunities to build the structures of that knowledge in their own brain through whatever they're doing. So building something and thinking about it. And Seymour went a step further and said, well, actually, if they build an artifact in the real world, right, that's even better for helping them build the structures of the knowledge in their brain. And that's why we have maker spaces now. It was work like this. But in Logo, you could build your own chatbot. Maybe it'd be sort of quasi AI chatbot. You could build graphical programs. It was beautiful because you could do recursion in this language. You could do music, so you could do like fractals really easily, or you could have the children program a computer-aided instruction system that would then teach their younger brother or sister math facts or something like that. So in other words, instead of the computer programming the child, it was the child programming the computer. And one of the things that Papert was known for, because he was a mathematician with an extreme interest in AI, was you can't think about thinking, which is what you're doing when you're doing research in AI. You can't think about thinking without thinking about something. So you need a problem domain to be working in. And he also would make observations. He would interview children of various ages and so on. And one of the things a child told him is that trees make the wind by flapping their branches. And rather than like, oh, you're wrong or whatever, he realized, well, actually, it's a pretty reasonable theory if you're, 7 years old or something like that. And that's consistent with your own experience and observations. The other thing about this that was kind of interesting, most people don't realize, is that Logo was taking the language that was used in AI at the time, which was Lisp, and basically putting training wheels on it so the syntax wouldn't scare children away. But you could do full-on AI programs using Logo. And so the idea there was the way to use AI in education was let's help children build AI systems. But there were other approaches, and this is one that I worked on as well. I was a graduate student working, while I was at MIT, I was working at a think tank called BBN. BBN is actually somewhat well known, sort of the Boston version of RAND Corporation. They were very involved in building the technology for the early ARPANET, which later became the internet. And they also were an acoustics research company, and they're the ones that decoded the erased portions of the White House tapes from the Nixon administration, proving that he was, in fact, a crook. But in any event, this part I worked on had to do with using this stuff in education. And we built a system called Scholar. Now I say we as that I was a graduate student part-time, working on it, but I'm going to talk about the part that I worked on. So this was a system that tried to provide a mixed initiative. First of all, what does that mean? That means the student can ask a question and get an answer, or the system can ask a question to kind of assess the student's knowledge and help them, maybe guiding questions to help them think of things in the sort of Socratic notion that probably the knowledge is in your head and you just need help getting to it, right? But anyway, a Socratic dialogue that supported, first of all, logical reasoning. You could look things up on the map, whatever. But one of the things we realized as we studied human teachers is that you have to go beyond logical reasoning. There's a notion that we would call plausible reasoning. Plausible reasoning was studied a lot by a guy named George Polya, who was a mathematics professor at Stanford. So plausible reasoning would allow you to reach conclusions about things that you could not be certain, but nevertheless you would usually be right. So I have an example here, and I happen to work on this example quite a bit. It was sort of my test example. And that was, a student might ask, is rubber an agricultural product of Guyana? They're learning about the geography of South America. Not just the geography in terms of, how far apart things are or whatever, but how, for example, the mountain ranges cause, rainfall, and all of what are the products and why are those products there because of the weather conditions, and all those kinds of how and why questions. So in any event, the student asks if rubber is an agricultural product of Guyana, and the scholar system looks in its database and it doesn't say that it is. But it doesn't just say no, and it doesn't just say, I don't know. Right? When it comes back and says, it took a lot of work to get a system to reason this way, is that, well, I know a lot about Guyana. I know what the main agricultural products of Guyana are. They're sugar and lumber. And I know a lot of other South American countries where rubber is an important agricultural product. So I can at least tell you that it's probably not a very important product of Guyana. Now, this was a system in the 1970s doing that kind of reasoning. So AI didn't just happen in 2022. It's been going on for a while, but it was a lot of hard work to build a system that could answer that, one pattern of question correctly. I don't see any questions so far, so I'm going to just keep going. Okay, well, how do we build those systems? Well, this architecture might remind you, if you've done some object-oriented design and so on, a sort of model view controller. But this was before we had that idea. But besides having an expert system, and we're going to talk more about the modern systems, but if you look at something like ChatGPT, as powerful as it is, it only corresponds to one of the modules that we thought were necessary to build a useful educational system, an intelligent tutoring system out of AI. Right? So how did the expert system get built? Well, what we did is we had human domain experts. So if we were building something like mycin to treat bacterial diseases, we would have human doctors sitting there, and they'd be asking us questions like, "What was the site of the wound?" and "Did you run this test? And what was the result?" and so on, and having them talk out loud, not just about telling us what they needed and so on, but why they were thinking they would need that, and what question they wanted to ask next, and whether that the answer to that question caused them to change what they were going to ask next, and so on. And we would model their protocols using something like if-then rules. So if the student has this, then ask that kind of questions. So we basically build a model of the human expert in the form of if-then rules. So, pretty simple kind of programming. Sometimes there were more sophisticated things that you needed to do, but that was it. Now, if we just gave the expert system to students, or in this case, it might have been medical students, it wouldn't have been that educational. It wouldn't have been that helpful for them. It would somewhat helpful, But we really felt that, especially if you start to look at lower grades and so on, there's a lot more that you need. The next thing you need is you need to have some understanding of what's going on in the student's head. What does the student think? Why did the student make that mistake? And we realized that because we understood well enough how the expert system worked, we could basically build a student model as a flawed variation of the expert system. So maybe it's almost the same, but it's missing some important rules. Or maybe it's got some extra rules that aren't right and should be removed. Or maybe it's got some rules that are almost right, but a little bit buggy, right? And we inferred that by watching the student behavior as they would try to do the task and what they would say. And so we had basically two versions of the model. One is like a buggy version and one is a correct version. We try to figure out where is the problem and is there one part of it that's causing, sometimes one bug can cause, 10 wrong answers, right? And each of those was talking to what you might call the controller in an object-oriented design model view controller approach. And that was the tutor. And the tutor was what the student was actually talking to. So we constructed the tutor not by talking to doctors and not by talking to students, by talking to master teachers. What a concept. Ask the teachers to help figure out how to do this, And we built heuristics because we wanted to know things like, well, when should we intervene if they're going down the wrong path? Or how long should we wait before they have the frustration of realizing that they're completely off track? When should we give a hint? Should we just ask a leading question? Should we maybe offer an analogy? And we don't have much of that, if at all, in any of the modern systems yet. So part of my message here is, stand on the shoulders of giants and don't completely reinvent the wheel, right? How come, the people trying to build these systems today have not read about any of these older systems? We're probably the worst discipline. Computer science is probably the worst discipline ever in not being aware of where it came from and what the history was and what we already know. So anyway, that's an architecture that probably could really help what we're trying to build today. Obviously, it might not be if-then rules. It might be things that are more like transformers and so on. But still, having these notions could help organize it so it's more effective as a teaching system. Right? How did we get to where we are today? What made that possible? Why didn't we continue down that path? Well, one reason we went down the symbolic path of building them by hand and not trying to do learning, because a lot of people thought, well, maybe we should be doing learning, was a book by Minsky and Papert, that same Papert, right? They had done a study of a particular single layer perceptron by a guy named Rosenblatt, and written a book that basically proved all the things it couldn't do, right? It was called Perceptrons. It was a very, very fascinating book. But people read that as saying, therefore, neural networks in general were a bad path. We shouldn't go down that path. And of course, they hadn't looked at multi-layer networks at all. And that turned out that when you open that door, a lot of things change. You do a lot because of the sort of hidden layers in the middle that they didn't say wouldn't work. They just didn't investigate it, So, but also, I mean, we had some huge other technology things that came along that made new things possible. The biggest one is probably the internet, because it provides just access to vast online data sets. So you need tons and tons of data to build large-scale, reliable, systems and train them. Right. Another one, which is named after Gordon Moore, from the CEO of Intel, is his law. He actually said computer power doubles every 2 years. And by computer power, what he meant is how many silicons can we fit on a square inch of silicon? How many transistors, rather, can we fit on a square inch of silicon? Turns out he was wrong, but not the way you might think. It was actually every 18 months. So that enabled computers to analyze vast amounts of content because we could have so much capability, so many millions of transistors. I mean, the iPhone in my pocket is way more powerful than the PDP-10 computer that I did my dissertation on. There was also huge demand for industrial applications, such as in ATMs, you could eliminate bank tellers. And of course, yeah, they're trying to eliminate jobs. That's a problem, right? or being able to have speech recognition that actually worked. Another thing that happened is once people began to realize that maybe there's something here that we kind of, because they had walked away from AI, and then basically, if you were trying to do AI like I was, it was really hard to get funding, because it was like, oh, these things are too hard to build. They take too long, they're fragile. They only work in very small spaces. But then when they said, well, maybe that's not going to be true anymore, venture capital started to arrive, and the winters ended, and AI started to really take off. And it didn't really catch the public eye till about 2022, but the venture capitalists were watching a lot of these AI companies before then. The other thing is accessible programming languages. I happen to love Lisp, but when I've taught it to students, they found it difficult. Whereas Python can do pretty much the same things, much easier to learn, much easier syntax, et cetera. And it's got all sorts of libraries, including libraries like TensorFlow and what have you, that allow you to build AI systems pretty easily. Now, something that was not missing back in those days was what's called Bayes' theorem. Basically, how do I calculate the probability of something given my base probability and the new knowledge that just arrived? Not a big deal, and anyone who's doing data science and statistics knows about it, right? But realizing that you could use that to do back propagation, to go back and fix the weights in a neural network, to say, wait a minute, if you change that weight, now I'm more likely to get the right answer. That became really important. There's another thing that happened is that a lot of the AI stuff from the early days was pretty good at cognition. I mean, you saw some systems that actually worked pretty well, but they were terrible at perception. Perception was really hard. And if you think about how humans work, we can only kind of think about one sequence of words and so on at a time. So it was a one at a time kind of processor. And anybody who thinks they can drive their cell phone, or drive their car and watch their cell phone at the same time, there's definitely a chance of an accident, right? But perception is a little different. And perception is many, many things happening at once. In fact, if you're in a restaurant trying to have a conversation, you have what's called the cocktail party problem, which is you hear so many conversations, it's hard to follow the one you're interested in, right? So perception is more parallel oriented. And I think that's, not a coincidence that tends to work better on, with things like these neural networks. So for those of you who haven't already heard this, they're obviously inspired by human neurons. And a human neuron looks something like this. The dendrites are basically the inputs. That's where you get information from other neurons or from possibly, essentially sensors downstream. And a neuron can send information to other neurons over what's called an axon. And the axons can connect to multiple neurons. So you can see how you can very quickly build a fairly complicated system, right, out of this kind of material. Now, that's not how transistor-based electronics are built, but you can build some of the same kinds of things in a logical sense. And so starting from there and saying, well, what if we have, millions of them or billions of them? That's way different than what we could have possibly done in the 1970s, right? So now we're starting to say, okay, hidden layers, that's part of it. So here's just an example of something that children can learn. It's called the teachable machine. And an example activity would be to say, let's take pictures of cats and pictures of dogs and see how many pictures of each it takes to where I can show it a picture of a dog or a cat, and it'll correctly identify which it is, right? And of course, you try real hard in your data set to do things like find dogs that kind of look like cats because they're smaller, or find cats that kind of look like dogs, and so on, to make sure that it's trained on subtle features, perceptual things that, you might not even think, if you were going to write the program by hand to do it, you might not even think to have maybe a feature detector for it. But the neural networks with enough nodes will eventually pick up that feature somehow. On challenges, it's hard for us as even the designers to quite understand how did it pick it up and which of these many neurons actually represents that feature, right? Or is it even a feature that we have words to describe, So, but anyway, that's the basic idea. Every time you get it right, you adjust the weights to make it even more likely. And every time you get it wrong, you adjust the weights. to make it less likely that you would get that same wrong answer on the same data the next time. Okay. And so they teach them a machine's an example, and you can use it for images. You can also use it to classify speech in a limited basis. But if we're trying to, for example, teach the next generation about AI, because they're going to live in a world that is dominated by AI, and they need to at least have an understanding of what's going on. They can train it, with their own pet at home, and a bunch of other pictures, and they can begin to get a sense of how that works. Mm-hmm. And of course, we have new things like DALL-E, which is an image generator. You give it a text description, you get back a picture, like the picture at the bottom of the screen that was generated by DALL-E, I think version 2. Version 3 is not directly available as an app on the website, but you can go to ChatGPT Plus as an API. It's also available for free in Microsoft Bing, if you like Bing as a web browser. And then, of course, ChatGPT. So it's generative, it's pre-trained, it's based on a large language model. And I think the operative word is large. So, I mean, one of the issues, and I didn't even think to mention this in my slides, but one of the issues is building them requires large amounts of carbon. And so some of this work, if it's not really solving an important problem, is kind of wasteful and bad for the environment. But it's pretty interesting what it can do. Okay, it's basically based on, generating the next token in a sequence based on all the previous tokens, right? Okay, so a few things about ChatGPT. Okay, it's amazingly capable. Given when you think about how it works, you think, well, that shouldn't do it, but it does. Right? But it's looking at millions of features. Sometimes it generates nonsense. Sometimes it generates offensive content, and yet it passed the bar exam. It also, and this is one that, in terms of what should we make students learn computer science, is passed the level 3 software engineer coding exam for a Google job description. It's valued at $180,000 or more in annual compensation. That's mind-boggling, right? And certainly can do all of the problems I assign in my introductory computer science classes. Yeah. But yet, if you give it a simple arithmetic problem, it may get it wrong. It may be completely stumped, and it hallucinates. Sometimes if you ask it to write a little paper for you, it'll write a paper with references in it. When you go and check those references, and they're bogus, they don't even exist. Right? So it certainly creates challenges for assessment in schools. Bottom line, though, it's not artificial general intelligence. It's this sort of interesting thing that can do amazingly intelligent things sometimes, right? It's certainly not self-aware, and it's buggy. So where do we go from there in terms of education? Do we want to have a teacher that sometimes tells the student things that aren't true? Well, actually, human teachers do that too. Maybe not as much in the area that they're specialized in. But here's an example. I'm thinking back to learning from my grandfather. So I asked ChatGPT, I'd like to have a function that calculates the square root of a number. This is sure a whole lot easier than the way that I did it when I was a child. All right, but this, right out of the box, perfect. Now, yeah, what it's doing is looking at everybody's GitHub repos, in the world, right? And so it's not hard to find it by various, similarity metrics and so on. But that's pretty impressive, and it's very tempting for students who are first learning Python. So it can do useful things. An example is making a robot that can disarm a bomb so that a human, doesn't have to go in and take a chance of being blown up. It can drive trucks 24/7, although there's a certain chance it might run someone over, but a human might too. It can explore potential cures for diseases faster than human scientists. It can recognize speech and then do the appropriate commands. So that's useful when you're driving or hands busy. If you're quadriplegic, might be extremely useful for them to be able to convey and get things done. Can recognize objects and scenes, such as driving a vehicle, but it has to be trained on enough examples. And we have to be careful about the examples because, for example, it's been shown that an automatic, self-piloted vehicle is more likely to run you over if you are black than if you are white, especially if you step slightly outside of the crosswalk. So we have to think about some of the things that happen in these systems and do a lot more research before we, have the big celebration, I guess. But certainly one of the things is, well, it could act as tutors for students. It could also be a tool that students could use to build things for their own use. And I think that's an important thing to do so that they grow up not just literate, but fluent about the world that they live in. But individualized instruction, but we need more than just ChatGPT. That's the expert system. We need the student model, and we need the tutor. And the systems that are being put out on the market today don't have those other important modules. So there's some issues. AI in general, I mean, there's tons of deployed applications, including automated military weapon systems. Imagine ChatGPT, and I've seen this behind the closed doors, mounted on a fairly agile mobile robot, and armed with really high-end powerful weapons, and then it has a hallucination. So we have to be careful about what we're doing, or we get some of the tragedies that we see in the Middle East and so on. Okay, let me move forward here. I'm having trouble getting it to move forward. Give me a second. Oh no, not a new slide. Darn it. Go to a slide. Thank you. There we go. Okay. So career paths. Well, and especially I know a lot of you are graduate students in data science. So there's tons of jobs just in, analyzing data scientist, data analyst, data engineer. There's also AI engineers, machine learning. There's a lot of career possibilities. I know the job market's been tough recently, and I'm sure many of you are painfully aware of that. But it's always been the case with high tech that there are busts and booms, and there was the internet bubble and it burst and there were no jobs for a while. It's coming back. One of my students from a couple of years ago just joined Apple after having to wait a while before they decided to start hiring again. But AI research, but one of them is instructional system designer. And that's it. If you think about something like Canvas, I mean, there's a huge, interest in being able to build systems that can help you learn things. And it might be used by a human teacher, but it still also can be used partly in a in a self-paced way. So there's value in both of those things. What do you need to know? Well, you certainly need to know some computer science, algorithms, data structures, complexity, so that when you build something that has to go at scale, it doesn't suddenly go exponential on you. You need to know some discrete math. You probably need to know some languages. But here's one of the things, is that right now the languages are Python, R, C++, Java, obviously object-oriented design more generally. It used to be Lisp. If you think about it, when I was a graduate student doing AI, not one of these languages that are currently mandatory, basically, existed. C existed, but not C++. Everybody used Lisp. Right? Now, hardly anybody uses Lisp. And I promise you, 10 years out of getting your master's, or if you go on and get your Ph.D., people will be wanting you to use a different language than the ones that you learned in graduate school. So that's just what we need to learn, is not just the language, but kind of the meta thing of, what do all languages have in them, and what am I looking for when I'm learning a new language? And the ability to rapidly learn new things. Right? So learning to learn is what you actually really want to be able to do. I mean, one of the things that, in terms of job opportunities, well, there's job opportunities to do things like be the one who deals with big data. Right? I mean, if you have these billions and billions of documents and so on that you've collected from the internet, it costs a lot of money to store them someplace, and so being an expert on just how to store the stuff, databases and beyond, The other thing to know, and this is something that some of the high school students I talked to earlier were asking me, is that high-tech employers, it used to be, well, I can't go into this field because I'm not so good at math, and I'd have to have a Ph.D. to get a job at Google or something like that. Actually, the high-tech employers are increasingly less concerned with degrees. I mean, it certainly helps, right? But they're less concerned with like your SAT scores Again, it helps, right? They want to know, show me a portfolio that evidences your ability to innovate, your high-tech skills. What kind of programs have you written? What kind of inventions have you made? Do you have people skills? Are you committed to lifelong learning? Because that's what makes a good employee. And yes, it doesn't hurt to have, a couple of initials after your name. But there are plenty of places. I mean, a good example of this, for those of you know the history of like the invention of the graphical user interface and so on, Xerox PARC used to hire people who were, really, really innovative and good at programming and able to invent things, devices, for pointing, what have you. Didn't necessarily require them to have a degree, and they ended up making a huge difference in the world. So, okay, I notice I'm getting a little tight on time, so let me move forward. I haven't seen any questions. I hope this is making sense to everybody. Here's an emerging skill, or at least a lot of people think it's an emerging skill: prompt engineering. So I actually went to ChatGPT, and the first time I did this, I asked, assume I'm a high school student interested in AI careers. Briefly tell me about prompt engineering jobs. And I got this huge, so basically, it wasn't sufficiently prompt engineered, if you will, and it was not useful to me because it was so large. So then I went back and I changed what I asked. Here's my second try. Now I say, briefly tell me, first of all, and specifically that do not require a CS degree. I got a paragraph. The paragraph is reasonable. So I do need to know Python or Java and whatever. It tells me what I really should focus on if I'm interested in using that kind of a skill. The question is, I don't know the answer, will this particular skill survive the test of time? Maybe not. Why? Because maybe whatever replaces ChatGPT, won't, require so much care to how you ask it the question, because maybe it'll be smart enough to figure out what you meant. Maybe. One thing that I think is really, really important, whether you're in computer science or data science, or even if you're going into management, but you're going to be managing technical teams, right? Bugs. Bugs are good. Now that sounds strange, especially when you spend a lot of your time trying to get rid of bugs, right? But first of all, they're good in the sense of how you think about yourself when you make a mistake. Because when you say, I got it wrong, there's all sorts of negative emotions that actually impede your ability to move ahead and be successful. Whereas you say, I have a bug, but I'll debug it and fix it. It's a different feeling. And it's especially a different feeling for children who say, I'm bad at math. Okay. No, you're not. You just have a bug. Let's help you fix the bug, right? And when you find the bug, maybe it takes you 2 hours, maybe it takes you all night, to find the bug. But when you find it, it's this aha moment that, oh, that's how that works, right? That you wouldn't have gotten if your code had worked the first time, which sometimes will work the first time, but not that often. So especially, I think one of the reasons that learning to code is good is because it gives you the opportunity to experience bugs and have those aha moments. I tell my students in my Java course, collect your bugs, put them in a journal. Let's make a taxonomy. Here's one, off by one error. Here's another one, not incrementing the counter loop, the loop counter. Here's another one, having the steps inside the loop out of order. Okay, more advanced one when you're learning data structures is aliasing an element in the data structure and then later clobbering it, right? And you can go on, right? So I want people to appreciate the variety of bugs. So I actually award little plastic bugs to my graduate students when they have an interesting bug, and also sometimes when they answer a hard question or something. And here's one thing I can say is that ChatGPT will come and go. I think it's pretty interesting where it is right now. The art and science of debugging will not go away because of ChatGPT, which, by the way, has some bugs. And another little observation is, as you can see from the car down here, sometimes serendipity comes into play, and what you thought was a bug turns out to be a feature. And so debugging is a wonderful, wonderful thing to focus your attention on. There's lots of societal challenges, and I think most of you know about some of these. So in the interest of time, I'll be very brief. There's bias, not so much probably in who wrote the algorithm or something like that, but in the the data itself coming from the internet. And so like if you're a Black person like Joy was, and you try to open your phone by looking at it, it doesn't recognize your face. If we had more people working at Apple who were Black and female, and not just in like secretarial roles, but in software engineering and so on, we probably would have noticed that before the product was out on the market. I worked for Apple for 10 years. Most of the people there wanted to do good things for the world. They didn't want to deliberately have something go out that was biased, but we need to pay more attention. There was a system in Florida that would predict a double the number of false positives when asked about potential recidivism for a candidate for probation. If you were Black, you wouldn't get probation. If you were white, you would. And it wasn't based on anything in reality. They were false positives. Bias in recruiting. Amazon's job screening tool used to favor males. There's deep fakes. I think you've heard that term before. I have a wonderful example of Nixon seemingly saying that the moon landing was faked, right? And it's so convincing that people will believe it when they see it. That was done at MIT to illustrate the problem. But the biggest thing may be labor disruptions. We're going to hugely impact labor. Yeah. So, and this is just a list. This was from a while back, 2013, of job descriptions, likely to be impacted. And a lot of them were sort of like things like an Uber driver. It seems like a no-brainer that Uber drivers are in trouble, right? And it won't help to go over to Lyft. I mean, that's not the problem, right? But now we're sitting there going, well, what about law clerks? So, pass the law test. What about entry-level coders? Because, I mean, ChatGPT does not do so well on really hard software engineering projects, but it does fine on kind of entry-level problems like you see in, a beginning class. So, maybe we're not going to be writing our own code anymore. Let me go to let's see. Go to the next slide here. Come on. Okay. So I'm going to skip that slide for the sake of time. What about the products that are out there? My advice, if you are in the position to possibly spend money on a product, as some of the teachers I spoke with earlier today is healthy skepticism is in order. And one of the reasons we know how they work and how they don't work, right? You shouldn't rush out and buy early products that claim to use AI to help you learn, right? Beware of the hype. And one of the reasons is that, especially right now, but this was even true when I started a company, it was like sprinkling some AI on a product that really is not an AI product is a good way to, a ruse basically to attract more venture capital. And so there's a lot of people saying that they have an AI system that helps you learn or whatever. And some of it is like very little AI and very large standard software engineering that isn't very complete yet. So be careful, and the questions I would ask are, were there master teachers involved in the design? There's probably no tutor module in their design, is it really just a front end for accessing ChatGPT with a little bit of syntactic sugar? And who has agency in the interaction? Is it the student or is it the AI? Who's in charge? What data are they collecting? Because in schools, there's all sorts of laws about what it's okay to collect. And if you're not compliant with that, you're going to end up having to turn the product off. And then there's, things like, is there any peer-reviewed evidence that the system actually improves the results on whatever it is you're trying to measure? And then sort of like the thing that's starting to be a real problem when you buy software is, are you going to own this product or are you renting it? And if you're renting it, are they going to keep doubling the fees every year? And finally, and this is the one that, I keep going back and saying, the people who are building these, do they know the history of this field? Because they have a hint button. When you push the hint button, which is always available, it tells you the answer. It gives you the whole solution to the problem. There's actually a product on the market that does that. Okay. So, and this is what Piaget would say about that. When you teach a child something, you take away forever his chance of discovering it for himself. Teaching means creating situations where structures can be discovered. So if the hint button came back and said, well, have you checked whether all your parentheses are balanced? More of a leading question. as opposed to just telling them, here's the code to solve your problem, right? Like I got from ChatGPT earlier, that would be much more educationally sound. So how should AI be used in K-12? Well, I think all students need access to it. I mean, I would say from even elementary school at various, grade appropriate ways, right? They need access to computer science. They need access to making. And now they really need access to AI. The original standards for AI that were finally issued a few years ago, sorry, the standards for computer science that were issued just a few years ago had literally 2 sentences about AI. And now we're realizing that AI is everywhere. And these students are going to live in a world that is run by AIs. They need to know more about it and understand how it works, not be intimidated by it, and also be able to say, okay, I understand why it said that and it's wrong, So one of the things I tell teachers who are teaching computer science is, of course, you have to code in order to learn computer science. But what you should be emphasizing is thinking like a computer scientist over routine coding. Right? Thinking like a computer scientist is something that is much more general than you've just learned Scratch or you've just learned Python or whatever. Debugging is much more important, but other problem-solving ideas that are powerful, not just in computer science, but in general, divide and conquer. Okay? Draw a diagram. Take the problem as solved. One of the ones that we programmed in Scholar, the lack of knowledge inference. Okay, well, I don't actually know that it's not true, but et cetera, right? Look for patterns. Try viewing it from a different perspective. Alan Kay, who basically invented the personal computer, said, point of view is worth 80 IQ points. So have you tried looking at the problem from another point of view? Debugging an almost right plan, which is easier than debugging a blank page, and so on. There's a whole book, well, there's books actually by George Polya about what he calls the science of heuristic. It's really, really important. That's the stuff that will carry you across. None of the languages that I learned in graduate school are in wide use today. And all of the languages that are in wide use today that I'm teaching at a university level even existed when I was a graduate student. So but the ideas about problem solving, those haven't changed. So languages come and go, but algorithms are forever. You don't have to suddenly say, okay, everything is AI now. Our whole school is going to be surrounded by AI, right? I say, to educators, plan a little and do a little, okay? Explore new AI offerings and try short experiments and see what works for you. But don't, do a deep dive investment in the latest tool, because in 3 months, it definitely won't be the latest tool. I have a couple of news feeds for what's happening in the AI world, and I literally need to take the summer off to read them because they've been coming in so fast this semester. And there's amazing features in free tools. For example, Snap, it looks like it's a block-based programming language, but it's definitely not a toy, and it's got something called NetsBlocks, which lets you do data science and so on, with like one block, right? And it goes out over the net and gets data for you. There's other things, App Inventor, which allows you to program phones and so on. ChatGPT, even ChatGPT, it can explain to you how to use its own APIs to call it from Python. So anyway, be thoughtful. And there's, of course, a big discussion about cheating, but we're also about out of time. And I think you all know the story. Basically, students should be learning about how to use these tools. And if they're able to effectively use them, they're going to outcompete other new arrivals in the job market who don't know how to use them. You should be clear about when it's okay to use them and when it's not. And trying to block access to it is stupid. The teachers need to be aware that the tools that try to tell whether you cheated or not generate a lot of false positives, which really undermines your relationship with your student. So here are what are considered the 5 big ideas in artificial intelligence by the K-12 world. This was just published, version 2 of this was just published by the California Department of Education. And I'm going to be really brief and just give you the headers: perception, representation and reasoning, learning, natural interaction. And at the center of all of it is, what is the societal impact? Many of these are things that you learn how to do. Societal impact are things that you need to think about and decide what are the consequences and what choices am I making that will make better or worse outcomes, right? But there needs to be more usage experience and there needs to be less mystery. It shouldn't be magic. We need to lift the hood. Students should be allowed to look under the hood. They might, if you take a car example, they may not be able to rebuild the engine, but it's a good idea if they know how to put air in their tires. Okay. So is AI going to destroy the world? Well, first of all, I think one more major idea is needed before we get anything close to resembling human understanding and performance. But even so, and I do think, by the way, that there's nothing inherently preventing silicon from doing what we're able to do with carbon neurons. So we may be at the beginning of what I would call the next Copernican revolution. It may be that the human brain is no longer going to be the center of the universe. People find that scary. I find it okay depending on how it happens and how we make sure that bad things aren't being done as a result. But it's something to think about. But we're certainly not there yet, and we may not even be close. We don't know. So I want to end with I talked about Seymour talking to children about what makes the wind, and me talking with my grandfather and learning about slide rules and so on. So last week, my grandson came to visit. He lives in Nashville, Tennessee, so I don't see him very often, but he's flown quite a bit. So we took him to the Aviation Museum, and we sat in the cockpit of a retired 747. And one of the things we talked about is he touched literally every single button, dial, and knob in the cockpit. We talked about, well, with autopilot, how many of these buttons and dials will still be needed in the next generation airplanes? But I also sent him home with a box of Legos, which specifically Mindstorms, which are the ones where you can program, right?
Mark, I think so.
Getting the wind as well. It's 5 years old. When the wind is fascinating, that's a wind tunnel. And he went back and forth and did that for quite a long time, more than 2 hours. But none of these things are going to matter quite as much when he gets to be older and looking at careers and so on. But I think what will help him make good choices is that I took the time to sit with him and wonder how and why. And it's, with a caring human who's passionate about STEM fields and AI and computer science, right? And that believe in you, that you can learn such things, right? That should foster enough curiosity to last a lifetime. So that's my parting thought. And I do have some references. If you really want to know about this field, this is the most recent book. Unfortunately, it's a little bit expensive. I think I've gotten the library to get a couple copies that you can check out electronically. Okay, questions, comments? I think I'm a couple minutes over. Is anybody left? Okay.
So I would like to really thank you, Mark, for your wonderful talk. And I think so people were really gained from your knowledge and with all these references and all that stuff. So all of the participants, I would like to thank you also. And do you people have any question or anything for Mark?
Yeah, I'm happy to take questions now. I'm not in a rush. I know it may be.
No, they have the class, Mark. They have the next class at 7.
Oh, they do. Well, we better let them go then. But they're
Okay.
also welcome to email me. Whatever. Yeah.
Okay. So thank you very much, Mark, again. I'll see you soon.
Thank you and take care. Bye-bye.
Okay. Thank you very much, everybody.
Thank you, sir.
Thank you. Bye-bye.
I'll share my slides also.
No problem.
Thank you.